Okay, so yesterday I spoke about the thermochemistry, and actually I was asking some people today, and I got mixed answers about the symmetry number of isopropyl radical. Is it 9 or is it 18? Okay, so I'm still waiting but I'll let you know before the end of the week what I think it is. All right. So I'm going to talk about chemical kinetics and first and second order reactions, kinetics in flow reactors, plugged versus stirred. Then I talk about temperature dependence. Then I talk actually about pressure dependence. I should add that here. And then maybe some complex reactions and so on. Okay, so again, we go back to our example here. We put A into a container. It can react to produce B, and eventually they reach equilibrium. So A decreases in time, B increases in time, and then this first part we consider kinetics, and then this other part, equilibrium, okay? And just bear in mind, and I'll be showing it later today now, that there is no line as such, right? They're interconnected and they're linked through the thermochemistry, which I discussed yesterday, all right? And I'll give a little bit more on that today, okay? And it's kind of nice the way it's done. Okay, so if we look at the rate of reaction, we can see, and it just makes sense by looking at this diagram. I took it off Wikipedia, okay? You can see that, like, if we have green balls reacting with blue balls, and we have a few of them, then, and reactions involve collisions, then if we have a low concentration, we'll have few reactions, right? Whereas if we have a higher concentration, we'll have more reactions, okay? So the rate of reaction must be proportional to concentration. It just makes sense, okay? All you have to do is look at this diagram, and you can see that it makes perfect sense, all right? So the rate then is equal to the rate constant, or a constant times concentration. A is proportional to B, then A is equal to constant times B, okay? And in this case, the rate is equal to the rate constant times concentration, all right? So as a kineticist, really what I am is a rate constant determiner, ultimately. Because if we want to look at combustion systems, typically we know the concentrations that we're going to be starting with. What we want to know is what is the rate of reaction. And to determine that, we have to determine accurate rate constants, right? So as a kineticist, really that's my job, right? Determine the rate constant, and then we can get accurate rate, okay? And K is the rate constant. So don't mix up rate and rate constant, right? The rate is equal to the rate constant times concentration, okay? What we're interested in always, of course, is the rate, but what we have to determine to get that is the rate constant, or provide, right? Okay, so here's a little bit of chemistry, and I know probably most of you are engineers and have an engineering background, but just bear with me. They're fairly simple equations, right? So we have 5 moles of Br minus plus BrO3 minus plus 6 moles of H plus gives 3 moles of Br2 and 3 moles of water, right? And so say we put Br minus, BrO3 minus, and 6H plus into this container, right? We seal it, okay, and we just come back at a certain period of time, right? How can we follow the rate of reaction, right? So just think about it. So according to this equation, it says 5 moles, or 5 molecules, or 5 moles of Br minus, or atoms of Br minus in this case, plus 1 molecule of BrO3 minus, plus 6 hydrogen ions react together to produce the products, right? So in principle, we can either look at any reactant or any product and follow the rate of reaction, right? And so the rate is equal to minus 1/5 the change in the concentration of Br minus ion with respect to time, okay? And why is it 1/5? Because in every reaction, 5 Br minuses are consumed. right? So the rate of reaction is 1/5 the rate of change of Br minus with respect to time, okay? And it's negative because Br minus is decreasing in time. It's a reactant, right? And so dBr minus dt will be negative, and we have minus times minus will then be positive. So the rate is always positive. If something's happening, it's positive. So we have dBr minus dt will be negative, and we have a minus times minus that makes it positive. And then we have minus dBrO3 minus with respect to time, or minus 1/6 dH plus with respect to time. And all of these are equal, as are, then we can look at the products also. 1/3 the rate of change of Br2 with respect to time, because, again, 3Br2 is produced in every reaction, okay? So if we measure, let's say we come back after a period of time, and there's 9 Br2s in the container, we know 3 reactions have occurred, right? And all of these are equal. And we can follow the rate of reaction by looking at any one of the reactants or products, or all of them, whatever you want, right? But we can follow it, okay? So where do we determine the rate law? The rate law comes from experiment, okay? And if I just go back here for a second, I have this general equation. The rate is equal to a constant times the concentration of reactants, right? So that's our general rate law, always, for a reaction. So if we look at this reaction here, the rate is equal to a rate constant times the concentration of Br minus to the power of alpha, BrO3 minus to the power of beta, and H plus to the gamma, right? And so the rate is equal to the rate constant of Br minus to the power of 1, BrO3 minus to the power of 1, and H plus to the power of 2, right? So it's actually not equal to the stoichiometric coefficient, right? It's not 5, 1, and 6, right? So it's actually alpha, beta, and gamma. And we have to determine alpha, beta, and gamma by experiment, okay? But we can't take it from the stoichiometric coefficients, okay? We can, and I'll just clarify that right now, but I'll be coming to it again and again. If the reaction is elementary, if it occurs as written, then you can take the stoichiometric coefficient, right? But it's wise not to assume that it's elementary unless you're told, right? And then you cannot assume the stoichiometric coefficients, okay? Okay, so in general then, if we have n moles of A and n moles of B giving us P moles of X and Q moles of Y, we can say the rate of this reaction is equal to the rate constant times the concentration of A to the alpha times B to the beta. Actually, it's not entirely true. And I'm just going to take a step backwards for a second, right? It's not entirely true, right? Because this is the rate, and we should write Kf here, the rate constant in the forward direction times the concentration of A to the alpha times B to the beta, minus K reverse times X to the gamma and Y to the delta, right? Because they'll be reversed. So the net rate will be the forward rate minus the reverse rate, okay? But as far as you're concerned, until I tell you otherwise, what we're doing is we're looking at the very early stages of reaction here, where you have a very high concentration of reactants and you have a very low concentration of products, right? And if the concentration of the products is very low, then the reverse rate is virtually zero, okay? And it can be ignored, okay? So just assume that we're not close to equilibrium, okay? We're at the very early stages of reaction when I'm making all these claims and saying all this, okay? All right, so, and then we have this general rate then, rate law, and so the rate is minus 1 over m, the change in concentration of A with respect to time. It's minus 1 over n, the change in concentration of B with respect to time. It's plus 1 over P, the change in the concentration of X with respect to time, and plus 1 over Q, the change in concentration of Y with respect to time. And this, and this rate laws are all equal to one another, right? You can write it as any one of those equations, right? right? And follow the rate of reaction with any one of those equations. Okay. So the units of rate is normally concentration per unit time. In SI units, it's moles per meter cube per second. More practically, it's moles per decimeter cube per second. Okay. So typically, we find out by experiment what alpha and beta are. We will be given this in the equation, so we don't do that by experiment. That'll be, we just balance the equation, right? But you do not take the stoichiometric coefficients, right? You get the order with respect to each reactant from experiment. And I'll show you how to do that a bit later, okay? And then the order is the sum of the partial order. So if the reaction is alpha with respect to A and beta with respect to B, then the total order is alpha plus beta, right? And then the rate constant is a K subscript N, and the rate is equal to the rate constant when all the concentrations are unity. Okay, again, that's not, okay. So here we have some experimental rate laws. For instance, we have 1 CO plus 1 Cl2 gives COCl2. But the rate of this reaction is equal to the rate constant times CO to the power of 1 times Cl2 to the power of a half. The order of this reaction is 1.5 or 1.5 order, right? But we can tell immediately that this reaction is definitely not elementary. Why? Because it's not 1 and 1, okay? So it's definitely not elementary, okay? Now, here we have H2 plus I2 giving us 2HI, right? And the rate of this reaction is equal to the rate constant times H2, the concentration of H2 times the concentration of I2. It's first order with respect to hydrogen, and it's first order with respect to iodine, and it's second order overall, right? So alpha is 1, beta is 1, the total order is 2, right? And here, but actually this reaction is not elementary either, even though it looks like it. It's not, okay? And then here we have H2 plus Br2 giving us 2HBr. The rate is equal to the rate constant times the concentration of H2 to the power of 1, Br2 to the power of 1, divided by this expression here. So in this case, the order is undefinable, right? Because it's too complicated. It's undefined, okay? Or none. Okay, so how do we determine the rate law? We determine it by integration. We can do it by trial and error, but the trial and error is not suitable for multi-reactant systems, but it's the most accurate, okay? Sorry, so, but with integration, we have to assume it's first order and check to see, does it obey first order kinetics? And if it doesn't, then we assume second order, does it obey second order kinetics? And if it doesn't, then maybe it's zero order or something like that, okay? But typically, most reactions are either zero or mostly first or second order with respect to reactants, okay? That's a general rule of thumb, okay? And then we have the initial rates. It's best for multi-reactant system, but it has lower accuracy to the integration method, okay? And then we have isolation or flooding, and this is a composite technique. So I'm going to show you examples of all these different techniques to determine the rate law of reaction. Okay, so for a first order reaction, if we have A moles of A giving us products, then we have minus the change in concentration of A with respect to time is proportional to the concentration of A to the alpha. Okay, I'm sorry that it's lost the alpha for whatever reason. Okay, and where we say the concentration of A is equal to the number of moles of A divided by the volume, where we assume the volume is 1. So we're interchanging moles and concentration, essentially. And by assuming that we have unit volume, or per unit volume, okay? So we have the change in concentration of A with respect to time minus the change in concentration of A with respect to time is then equal to the rate constant times the concentration of A to the alpha, okay? And so if a reaction is first order, alpha is 1. It's first order with respect to A, And if that's the case, then we have the changing concentration of A over the concentration of A to the power of 1 is equal to minus the rate constant times dt. Okay? And we integrate that, we get the log of A from A0 to AT is equal to minus K times T. Okay? I think this is fairly straightforward for everybody. Okay? And then we have the log of A at any time minus the log of A at time 0 is equal to minus K times T minus T0. But typically, T0 is 0. Okay? So we have the log of A at any time is equal to the log of A at time 0 minus KT. So we have Y is equal to C plus mx. So, in other words, if a species obeys first-order kinetics, if we draw a graph of log of its concentration at any time versus time, we should get a straight line, the slope of which is minus the rate constant, and the y-intercept is log of A at time 0. Okay, if it obeys first-order kinetics. Okay, and here I've plotted it. So we have log of the concentration of A versus time. You can see here the R squared is very high. It's not actually written here, but you can see that the line is touching most of the points there. And the slope of this is minus the rate constant. So the rate constant for this reaction is 1.49 times 10 to the minus 3, and then per second, right? The units of the log of A is unitless. The units of the x-axis is per unit second. Okay? So the rate constant is 1.49 times 10 to the minus 3 per second in this case. Okay. So, but if we look at this reaction or this equation in a different way, we can write it, I wrote it like this, but I can also write it like this. We have log of A at time t all over the concentration of A at time 0 is equal to minus K times T. Okay, so we have the concentration of A at any time divided by the concentration of A at time 0 is equal to the exponent of minus KT. Or the concentration of any time at any time is equal to the concentration of A at time 0 times the exponent of minus the rate constant times T. Okay, and so this is the equation actually that they use to do carbon dating. So if you want, you know, determine the age of the Curran shroud or whatever it is, right, for carbon dating, they do this. They work out, okay, the concentration of carbon-14 in the sample. And when they determine the concentration of carbon-14 in the sample, they can actually work out the age because they know the rate constant for carbon-14 decomposition and they know the concentration that it should be originally. Okay, so that's how they do it. Okay, this is just another plot of the concentration. I haven't plotted log concentration, I've plotted concentration versus time. And you can see that the concentration of A is decreasing exponentially with time. So again, that's an indication that it's first order kinetics. Okay? Okay, and then the half-life of a first order reaction, what's that? The half-life is the time taken for a sample to reach half its initial concentration. It's fairly self-evident. So if we then use this equation, we can then determine what the half-life is. Okay, so at the half-life, T is T a half, and the concentration of A is a half A0. So we have half A0 all over, half the concentration of A at time 0 over the concentration of A at time 0 is equal to minus the rate constant times the half-life. Okay, so again, the concentration of A at time 0 cancel, and we have the log of a half is equal to minus K times T a half. So the log of a half is minus K times T a half. The log of a half is minus 0.693. So the half-life is 0.693 all over the rate constant, or the rate constant is 0.693 all over the half-life, okay, for a first-order reaction, okay? And that's nice because if we know the rate constant, we can get the half-life, or we know the half-life, we can get the rate constant very easily, okay? And when is a first-order reaction finished? And the answer is never, right? But, okay, if we go back here, you can see that within 800 seconds here or 1,000 seconds, the sample has decreased to about, well, I don't know if this is the initial, yeah, it is. So it's about 80% or diminished or more, 80 or 90% diminished at that stage. Okay, so when is it over? Never, right? Okay, so that's first order kinetics, and this is by integration, right? For second order, we now have the concentration of A times the constant of A is equal to products. A moles of A gives products. Again, the expression minus the change in concentration of A with respect to time is proportional to the concentration of A to the alpha. Minus, so we can write, again, assuming we have unit volume, we can write the change in concentration of A with respect to time is equal to K times the concentration of A to the alpha. But this time, it's second order, so alpha is 2. Okay? So we put the power A to the power of 2 here, and we integrate that. So the integral of A to the power of minus 2 is 1 minus 1 over the concentration of A. And then we have to integrate that from the concentration of A at time 0 to the concentration of A at time t, and that's equal to minus the rate constant times t minus t0. Okay, so we have minus 1 over the concentration of A at any time, minus 1 over the concentration of A at time 0 is equal to minus k times t minus t0. Okay, and if we solve that equation down, we can say, right, a plot of 1 over the concentration of A at any time versus time should give us a straight line, the slope of which is the rate constant, and the y-intercept is 1 over the concentration of A at time 0. Okay, and that's if A obeys second order kinetics. Okay, and the reason this is a trial and error method is so you have to take first of all, you have to measure the concentration of A versus time. Then you have to plot log of concentration. If that doesn't give you a straight line, then you have to try 1 over concentration, okay, to see whether it's first or second order, okay? And then here, I've done it for this. So this is just some sample data that I had for ArSO2H. And concentration units are liters per mole and versus time, okay? And you can see here, the R squared is virtually 1 in this case. The line is going through the points almost perfectly. So the rate constant this time is 0.1374, okay? 0.1374 liters per mole per minute for the second order, okay? It's going to be inverse concentration per unit time, okay? Or the units, okay, for the rate constant. Okay, and then the half-life of a second-order reaction, we have 1 over the concentration of A at any time minus 1 over the concentration of A at time 0 is equal to K times T. So if we're at the half-life, the concentration of A at that is a half A0. So we have 1 over a half A0, and 1 over a half A0 is 2 over A0. Okay, I should say 2 over the concentration of A at time 0. Minus 1 over the concentration of A at time 0 is equal to K times T a half. Okay? And therefore, we have 1 over the concentration of A at time 0 is equal to the rate constant times the half-life, or 1 over the rate constant times the concentration of A at time 0 is the half-life. Okay? You can manipulate the equation whichever way. Okay. So that's integration in determining the rate law. Okay, and again, that's a trial and error method, but it's very accurate. Okay, so and it's either first order or second order, or sometimes maybe 0 order. What would 0 order mean? It doesn't depend on the concentration. Okay, it's independent of concentration. Okay, so here we have our example equation again. We have 5Br minus plus BrO3 minus plus 6H plus, giving us 3Br2 plus 3H2O. Sorry. Okay. The rate law we know always we can write that down in general is equal to the rate constant times the concentration of each reactant raised to some power, in this case alpha, beta, gamma. All right? So the log of the rate is then equal to log of the rate constant plus alpha log the concentration of Br, the initial concentration of Br minus, plus beta log the initial concentration of BrO3 minus, plus gamma log the initial concentration of H plus. All right? And then we can, okay, we'll just rewrite this again. The log of the rate, the initial rate, is equal to, we just move this over. We have alpha log the initial concentration of Br minus, plus a constant. Okay? So we lump all of the other species into a constant. Okay? And then we say, okay, so what if we, so now we have this equation, y is equal to mx plus c. Right? So we have, if we measure then initial rates of reaction, okay, and keep the concentration of BrO3 minus and H plus constant, and vary the initial concentration of Br minus, we can determine what alpha is. Okay? Because if we perform experiments and we keep the concentration of BrO3 minus and H plus constant, and we're just varying the concentration of Br minus, we can then measure the variation of the initial rate and measure it. Okay? And then if we plot log of the initial rate on the y-axis versus log of the initial concentration of Br minus on the x-axis, we should get a straight line, the slope of which is alpha. Okay? And then so we do that. Okay? And then we do another series of experiments where we keep the concentration of Br minus and H plus constant, and we vary the concentration of BrO3 minus, and we measure the rate of reaction. And then we plot log of the rate of reaction versus log of the concentration of BrO3 minus. We should get a straight line, the slope of which will be beta. Okay? And then we do a third series of experiments where we keep the initial concentration of Br minus and BrO3 minus constant. We vary the concentration of H plus, and we then measure the initial rate, and we then plot a graph of log of the initial rate versus log concentration of H plus. We'll get gamma. Okay? And then we can then independently determine what alpha, beta, and gamma are. And this is the initial rate method. Okay? So you're taking the initial concentration of the species and you're determining the rate law based on that initial concentration. Okay? Is that all right with everybody? So that's that. Okay, so here's an example. We have 2NO plus 2H2 gives N2 plus 2H2O. Okay, experiment number 1, the initial concentration of NO is 25 arbitrary units, whatever you want to use. Hydrogen is 10, and the initial rate is 2.4 times 10 to the minus 3 units, whatever that is. Okay, for experiment number 2, we have 25, 5, and the initial rate is 1.2 times 10 to the minus 3. And then for 3, the initial concentration of NO is 12.5. That of H2 is 10, and it's 0.6 times 10 to the minus 3. Okay. So we can deduce the orders with respect to NO and H2 and calculate the rate constant very easily. How do we do that? It's as simple as this. We have NO. So we have the rate of the first rate is equal to 2.4 times 10 to the minus 3, and that's equal to the concentration of NO, which is 25 to the alpha times 10 to the beta. Okay? And then we have rate 2 is equal to 1.2 times 10 to the minus 3, and that's equal to 25 to the alpha and 5 to the beta. Okay? And now if we put 1 over the other, so 2.4 times 10 to the minus 3 all over 1.2 times 10 to the minus 3 is 2, and that's equal to, these cancel, and then we have, it's going to be 2 to the power of beta. So therefore beta is 1. It's very simple. Okay? And then we can do the same for 1, sorry, what are we doing? 1 and 3. Okay, so if we do rate of 1 and rate of 3, okay, and that's equal to 2.4 times 10 to the minus 3, and this is 0.6 times 10 to the minus 3. And this is equal to, again, it's 25 to the power of alpha times 10 to the power of beta. And this is equal to 12.5 to the alpha and 10 to the beta. So we do this, and we have 4 is equal to 2 to the alpha. So therefore, alpha is equal to 2. Okay, very, very simple. Okay, so all we had to do was 3 experiments. We had 2 reactants. All we had to do was 3 experiments, and from that, we were able to determine what alpha and beta are. Okay, so in this case, alpha is 2 and beta is 1. So the rate law for this, the rate is equal to the rate constant times the concentration of NO to the power of 2 and H2 to the power of 1. Okay? And that's it. And then you can calculate the rate constant. You're given the rates, and okay. And okay, I've done it out there for you. And the rate constant is always 3.8 times 10 to the minus 7 decimeter to the power of 6 per mole squared per second, assuming that the concentrations are in moles per decimeter cubed. Okay, so I'm just assuming that the concentrations are mole per decimeter cubed and the time is seconds. Okay, so, and you can see in all cases you're getting the same rate constant, which you should, because it's constant. Okay. Okay, so then I think this is just obvious, but how would you measure the initial rate? So say you have A plus B giving you P and Q, okay? And you start off at time 0, you have 100 A's and 100 B's, and you have no P and Q. You just have 100 of each of the reactants. And then after 10 seconds, you'll have 99 A's, 99 B's, 1 P, and 1 Q, right? So you know 1 reaction's occurred, right? And so on, okay? How do you measure the rate? Well, the rate would be, you can do it with respect to A or B. It would be 99 minus 100, which would be minus 1. So it would be minus 1, which is 1 divided by 10, or 0.1 moles per meter cubed per second. I'm putting it in SI units this time, okay? But it doesn't, it doesn't matter, okay? And, or you could say, you could look at P or Q, and that would be 1 divided by 10, which is 0.1 moles per meter cubed per second, okay? So either way, you use reactant or product, you get the same answer, okay? But if you have a choice, which would you use? Product, okay, because I've written it there. But, okay, the way I always explain this is, look, I don't know about you, but, you know, it's not so bad now, but years ago, you know, at the start of the month, you get paid and there'd be lots of money in the account, and a fiver here or there didn't matter. But at the end of the month, when you're running low, a fiver here or there does matter, okay? So when you have lots of something, you don't really notice a fiver here or there. But when you don't have lots of something, you do notice a fiver here or there, right? So here you have lots of reactants and no product, right? So it's hard to see the decay in the reactant because there's so much of it there at the start. But it's easy to see the appearance of the product because there's nothing there at the start. So if you have a choice and you're equally sensitive to each of the reactants or products, it's best to look at a product, okay? So I think there's two things that I said there that equally sensitive to them is important too, because you may be very sensitive to a reactant and then it would be clever to follow the reactant, okay? So just be careful. And then, so the first method I had was integration, the second method was initial rates, and now isolation and flooding. And this is sort of a variation on the initial rates, to be honest with you. Okay, so here's a different example. I could use the same one, but just to mix it up a bit, okay? We have IO3 minus plus 8I minus plus 6H plus gives 3I3 minus plus 3H2O. Again, the rate law is equal to the rate constant times the concentration of each of the reactants raised to a power, okay? So the idea is just to use something different, but you're seeing the same thing. We're treating it the same way, right? It's the first reactant to the power of alpha, the second reactant to the power of beta, the third reactant to the power of gamma, okay? We haven't changed our approach, right? And so if we add excess iodate to the reaction mixture, okay? So let's say we have a lake full of iodate and we have a thimble full of the other reactants. Will we notice any change in the concentration of the iodate? And the answer is no. There's so much there that we won't notice any change in it, okay? And it's the same then with the concentration. Okay, so we add excess iodate to the mixture, then the concentration of the IO3 minuses is effectively constant, right? And then the rate is equal to K prime times the concentration of I minus to the beta times H plus to the gamma, where K prime is equal to the actual rate constant for reaction times the concentration of IO3 minus to the alpha. Because the concentration of IO3 minus isn't changing, we can multiply its constant times the rate constant to get a pseudo constant K prime. I'm not going to say pseudo first order, pseudo rate constant K prime, okay? And then we add excess acid, so we have loads of H plus, and then therefore H plus is effectively constant, right? And the rate is then approximately equal to K double prime times the concentration of I minus to the beta, where K double prime is equal to the true rate constant for reaction times the initial concentration of IO3 minus to the alpha times the initial concentration of H plus to the gamma, okay? And then what you do is you do a series of experiments where you have just a small amount of I minus, but it will vary from one experiment to the next, okay? And what you do is you measure, you plot the rate versus the concentration of I minus, or sorry, you plot the log of the rate versus log of concentration of I minus. And then you'll get beta, okay? Because log of rate is approximately equal to K double prime times beta times log I minus, okay? So if you plot log of the rate times log of I minus, you should get beta. So use integral or initial rate method as desired to determine what beta is, okay? But you can then isolate I minus by flooding the system with the other reactants. So that's why it's called isolation flooding, okay? Okay, so I said this a little bit earlier. For the rates of elementary reactions, the law of mass action applies. So if you have the rate of reaction is proportional to the product of the active masses of reactants. In other words, if a reaction is elementary, then it occurs as written, and you can use the stoichiometric coefficient. It's correct, right? So in other words, here we have 1A giving us P plus Q. The rate is equal to the first order rate constant times the concentration of A to the 1, right? If we have A plus B giving us C plus D, the rate is equal to the rate constant times the concentration of A to the power of 1 times B to the power of 1. and we have this reaction 2A plus B giving us E, F, and G. The rate is equal to the rate constant. It's the third order rate constant, I should say, times the concentration of A to the power of 2 times B to the power of 1, right? It's not, this 1, 2, and 3 doesn't mean that this was reaction 1, this is reaction 2, and this is reaction 3. It actually means that it's the first order rate constant, second order rate constant, third order rate constant, okay? And where does the order come from? It comes from the sum of the partial orders of the reactants. So here it's 1, here it's 1 plus 1 is 2, and here it's 2 plus 1 is 3. Okay, so that's where those numbers are coming from. Okay, so the molecularity then of a reaction, we have A giving us products, the change minus the change in concentration of A with respect to time is equal to the rate constant times the concentration of A. And so that's first order. That's unimolecular, sorry. Bimolecular collision, A plus B giving us P, that's equal to the second order rate constant times the concentration of A to the power of 1 times B to the power of 1. And then termolecular, we have A plus B plus C giving us products. The rate is equal to the rate constant, the third order rate constant times the concentration of A to the 1, B to the 1, and C to the power of 1. Okay, so no other reactions are feasible. No other elementary reactions are feasible, right? It's statistically highly unlikely or zero that you'll have more than 3 species arriving at the same place at the same time. And typically, actually, even termomolecular reactions largely rewrite the rate constant for those as being 0, okay, in general. Not always, but most of the time, okay? Okay, so here I said earlier that CO plus Cl2 gives COCl2, and the rate law of this reaction was equal to the rate constant times the concentration of CO to the power of 1 times Cl2 to the power of a half, okay? So you can tell that this reaction is definitely not elementary, right? Because the order is 1.5 order, okay? So what happens? So it's actually, this is the mechanism for that reaction. So we have Cl2 giving us 2 Cl radicals. That's a unimolecular decay or decomposition. And then a Cl radical reacts with CO to give COCl. And then COCl reacts with another molecule of Cl2 to give us COCl2, the product, plus Cl. And then one of the Cls that were left over from here plus one of the Cl that's produced here recombine to give Cl2. Okay? So steps 1, 2, 4 comprise the mechanism of this reaction. So it doesn't occur in one elementary reaction. There's actually 4 elementary reactions which explain this, the mechanism for the formation of COCl2. Okay, so what actually happens is, okay, so if we assume that steps 1 and 4 are very fast, and then 2 and 3 are slow in comparison, right? We can say, well, Cl2 giving us Cl plus Cl, and then Cl plus Cl giving us Cl2 are in equilibrium. Okay? If that's the case, then we can say, okay, well, Cl2 is in equilibrium with 2 Cls, right? So the equilibrium constant is equal to, not rate constant, no, equilibrium constant is equal to Cl, the concentration of Cl2 squared divided by the concentration of Cl squared divided by the concentration of Cl2. Okay? So the concentration of Cl is equal to the square root of the equilibrium constant times the concentration of Cl2. Okay? So, and then where do we have CO? We only have CO in reaction 2. So the rate of, what's the rate of the reaction 2? The rate of reaction 2 is equal to the rate constant for reaction 2 times the concentration of Cl times the concentration of CO. Okay? It's elementary, so it'll be Cl to the power of 1 and CO to the power of 1. Is that all right with everybody? Okay. So the reaction 2, the change in concentration of CO with respect to time, is the second order rate constant times the Cl to the power of 1 times CO to the power of 1. But we know that the concentration of Cl is actually the square root of the equilibrium constant for Cl2 giving us 2 Cls, right? Times the square root of the concentration of Cl2, right? So we have that for the Cl concentration. So actually the rate law is equal to the rate constant for reaction 2 times the square root of the equilibrium constant for Cl2 equilibrium times the square root of Cl2 concentration times the concentration of CO, right? So we predict that the observed rate constant is equal to the rate constant, the second order rate constant, which is the rate constant for reaction 2, times the square root of the equilibrium constant for the Cl2, giving you 2 Cls equilibrium, right? And actually, that was investigated, and it was proven that that was true. And then that proved the mechanism for that reaction, okay? So that's how it was shown, okay? Okay, so here's another complex non-elementary reaction. So you have acetaldehyde giving you methane plus CO, right? But traces of ethane, hydrogen, this is acetone, etc., are produced, okay? So there's traces of other compounds produced here, okay? The rate law is equal to, the rate is equal to a rate constant times the concentration of acetaldehyde to the power of 3 over 2, okay? It's 1.5 order. So again, is this reaction elementary, right? And the answer is no, because it's not 1. Now, if it came out that it was 1, would that tell you definitively, yes, it is elementary? And I don't think so, right? It may or may not be a coincidency, right? So you have to actually determine it, okay? But here is a possible mechanism. We have acetaldehyde giving us methyl plus formal radical, okay? And then the methyl radical abstracts a hydrogen atom from acetaldehyde to give methane plus this CH3CO radical. And that CH3CO radical then can decompose to give methyl and CO. So now you have methane and CO, the main products. The methyl can then recombine to give ethane. Or HCO can decompose to give CO plus H. H can abstract a hydrogen atom from acetaldehyde to give CH3CO plus H2. So we get H2. Or say if CH3CO combined with methyl, you'd get acetone, CH3CO, CH3. Okay? So that's how there's lots of other reactions other than what we list here going on in the mechanism. Okay? But the mechanism is a complex such that the order with respect to acetaldehyde is not first order, it's 1.5 order. Okay? And that shows that there's a mechanism. Okay? And this is, as I've said, this is not the complete mechanism. It's just partial. Okay? Okay. So should we take a break there? Are you all tired? Do you want to take a break, or will I go do temperature dependence? I'll do temperature dependence, and then we'll take a break then. Okay. So we have ethyl chloride here giving us ethylene plus HCl. And the rate of this reaction is equal to the rate constant times the concentration of ethyl chloride to the power of 1. Okay? So what do people, okay, so we have a rate constant, okay, measured at 700 Kelvin is 6.1 times 10 to the minus 5, right? At 727 Kelvin, it's 30 times 10 to the minus 5. And then at 765 Kelvin, it's 242 times 10 to the minus 5. Okay? It's unusual to write it like this, but the idea here is just to show, okay, this is 5 times bigger at 727 Kelvin, and then it's 40 times bigger at 765 Kelvin compared to 700 Kelvin. Okay? So the rate is, the conclusion is that the rate of reaction, or the rate constant, this is rate constant, is very sensitive to temperature. Okay. Now, how was this rate constant determined, by the way?
Experimentally?
Yeah, how? Okay, so what would we do? You're right, and I'm just trying to draw it out. I just wanted you to start thinking, because at the end of this, then we'll be able to determine the rate and plot rate constants. Okay, so I just want you thinking. I'm asking for a deliberate reason. No, you're right. Keep going. In. Not really. Yeah. We can track any one of the three species, but let's just say we track the reactant. Okay? And all we do is say, right, okay, we determined that it was first order. How did we do that? So what we did was we measured the concentration of C2H5Cl as a function of time, right? And then we just plotted log of the concentration as a function of time. We got a straight line, the slope of which was minus the rate constant. And then we did that at 700 Kelvin, and the rate constant came out to be 6.1 times 10 to the minus 5. We did it again at 727, and it was 5 times that. We did it again at 765, and it was 40 times that. Okay? But the way we got the rate constant was we just monitored the concentration of C2H5Cl as a function of time at each of the three different temperatures, and then we plotted log of the concentration versus time, we got the rate constant. Okay? I just wanted you to bear that in mind for later. Okay? So this is where we got the rate constants from to start with. Okay? Or at least it's one way, right? So, and just the conclusion anyway here is the first thing that we should take is that the rate of reaction is very sensitive to temperature, and a rule of thumb that use is that the rate approximately doubles for a 10 K rise in temperature. Okay? And I come back to that later. Okay? So the details of temperature dependence, and actually if you go back, Hood and Arrhenius, they were around the same time, and they pretty much came to the same theory, although we refer to Arrhenius, but I think Hood might have been beating him to it, but it's just Arrhenius is more famous about it. But anyway, one way or another, it's pretty much the same equation. Hood said that the rate constant is equal to a constant times the exponent of minus another constant divided by T. And then Arrhenius said, right, well, it's a constant. The rate constant is equal to a constant times the exponent of minus an activation energy all over RT. Okay, where R is the gas constant. Okay, and so he's the activation energy and R is the gas constant. So if we plot, and this is just then looking at here, we have rate of reaction versus temperature. You can see, look, if we're at low temperature, nothing's happening. And then in both the blue line and the magenta line, the reactivity starts at this temperature here. And then it goes up substantially in the magenta line, not as quickly for the blue line. So what's that saying? It's saying that this reaction, the magenta reaction and the blue reaction have about the same activation energy, but the magenta line has a higher A factor than the blue one. All right? And then the green one has a similar profile to the blue one. It goes up parallel with it, okay? It's slightly lower activation energy, or sorry, slightly higher activation energy, so should say, slightly lower rate of reaction. Then it increases quite a lot here at higher temperatures, so it has a higher activation energy, but also a higher A factor, okay? But once it reaches this temperature, it plateaus out and then keels over. So what's going on there, do you think? Well, it's probably, yeah. Probably not, I would say, because we're plotting rate versus temperature. I think, well, and it's kind of, there's a hint here, it's a green line, right? So it's probably some biological process, and you just killed your entity, and it can't react anymore because the temperature is too high, and it's keeled over and died, basically. All right, that's right, okay. And, okay, there's one thing here, just for my undergrads, I have these slides as well. And if you go to this website and you look at the cherry blossom front, so in Japan, the cherry blossom is very important, and they like to know when it's going to happen and so on. But if you look at the equation that they use to predict when the cherry blossom front is going to arrive, it's an Arrhenius temperature dependence. Okay, I should have introduced maybe kinetics by saying, look, why do we put milk in the fridge? Why do we put food in the freezer? Okay, to slow growth, yeah. And why like I was always kind of naive and silly, but you see in universities, the biologists will have freezers minimum minus 80, and oftentimes lower than that. Why? Because the bugs will be much less active at minus 80 than minus 4. I was always thinking, well, isn't minus 4 good enough? Because they'd be frozen. Well, it's just to slow things down really, really slow. So again, it's important, right? And in the springtime, why is there no growth in the wintertime? Because it's cold and the rate of growth is 0, or actually it stops in the autumn, okay? And then in Ireland, a number of years ago, we had a really cold spring, and the farmers couldn't put their animals out on the land. And then we had to import fodder from England and from France to feed the animals so that they could survive until the grass started to grow. Okay, so the growth of trees, plants, and all of that is dependent on temperature, and it's an Arrhenius process. Okay, so all of that is related. Okay, so and here's a picture of Svante Arrhenius, just so you see. Okay, so here we have the Arrhenius equation. We have the rate constant is equal to A e to the minus EA over RT. So a useful linear form of that is log of the rate constant is equal to log A minus EA over R times 1 over T. And now you can see, look, if we measure the rate constant, a number of rate constants, and we plot them on the y-axis versus 1 over T on the x-axis, we can get a straight line, the slope of which is minus EA over R, and the y-intercept is log A. Okay? So if we go back now, we had this at the start, ethyl chloride giving us ethylene plus HCl. The rate is equal to this expression here. We have these rate constants versus temperature. So if we plot log of K versus 1 over T, we should now be able to get the activation energy and the frequency factor for the rate constant for this reaction. Ethyl chloride giving us ethylene plus hydrochloric acid. Okay, and we do that, and we get, so we have log of A is 33.6223, and EA is 252.206 kilojoules per mole. Okay, so we have the rate constant is equal to 4 times 10 to the 14, the exponent of minus 252.206 all over RT. Okay, log K versus 1 over T. Okay, so this is the temperature, this is the rate constant for that reaction. So we have 1, 2, 3 temperatures. But now, given that and the linearity of this, certainly any place on this curve within the range of which it was measured, and probably certainly a little bit to the left and a little bit to the right, okay, we know the rate constant, and we can calculate the rate constant at any temperature, okay, from this equation. Okay, so and just to say then, I want to kind of hammer this home. So what we do to measure the rate constant is perform an experiment. We have the reactant, we plot log of its concentration versus time. If that gives us a straight line, great, then the slope is minus the rate constant. If it doesn't give us a straight line, then we plot 1 over the concentration. If that gives us a straight line, then we know it's second order, okay, to determine the order first, right? And then if we measure the rate constant as a function of temperature, we can get the Arrhenius equation, and then we can determine the rate constant at any temperature, certainly within the range of where we measured, and maybe even beyond it, okay? Okay. Experimental activation energies range from 0 to about 400 kilojoules per mole. Here are some examples. So here, for instance, H, hydrogen atom abstracting a hydrogen atom from HCl, it has very low activation energy of 19 kilojoules per mole. Okay? Whereas breaking a carbon-carbon bond in ethane has an activation energy of 368 kilojoules per mole. So it depends on the type of reaction what the activation energy actually is. Okay. Okay. And here's another problem, and it's something to think about. I just wanted, I include it deliberately just so you get a feel for it. Okay. So in consecutive reactions, the slower step usually determines the overall rate of reaction. Okay. So why am I talking about this? So diethyl adipate is hydrolyzed in 2 steps, right? So you get this intermediate B, and then you get the product, right? The Arrhenius equations are, the first step, the rate constant is 3.6 times 10 to the 6 times the exponent of minus 5,080 over T. Okay, so we've divided by R already, and we have an activation temperature. Okay, it's still an energy, but we've already divided by R. Okay, and the second step is 8.8 times 10 to the 5 times the exponent of minus 4,010 all over T. All right, and that's the second step. So the question is, which step is rate determining if the reaction is carried out in aqueous solution at atmospheric pressure? Right? And the answer is, it depends on the temperature. Okay? So here's the expression for the first step, and here's the expression for the second one. Okay? And so I've plotted them here, and there's a reason I'm showing you this now. So you see here, we have log of K on the y-axis versus 1 over T on the x-axis, right? So this is low temperature, and this is low temperature, and this is high temperature. Low rate of reaction, high rate of reaction, okay? And you can see actually that this step, the 8.8 times 10 to the 5 times the exponent of minus 4,010 all over T is faster at low temperatures, all the way up to about 800 Kelvin. And then they're about the same, and at temperatures above that, actually, the red line is faster, okay? And I chose the colors deliberately, blue for cold and red for hot, okay? So the blue, the cold one, right, is faster at low temperature, and then the red one is faster at high temperature, right? But what determines this is the shape of the curve, right? So the slope here is steeper in the red case compared to the blue case. Why? Because the activation energy is higher, okay? So what it's saying is, look, in the red rate constant, the frequency factor is higher, but the activation energy is always also higher, right? In the second curve, the frequency factor is lower and the activation energy is lower, okay? So which one matters? And maybe they're about the same. Well, they are the same at 800 Kelvin. But at temperatures below that, the one with the lower activation energy is faster. And at temperatures above that, the one with the higher frequency factor is faster. Okay? So, again, you have involved in, and I'll be showing it later today, involved in the rate constant, you have frequency factor or entropy and activation energy. So you have enthalpy and entropy, and altogether you have Gibbs free energy, right? And it's taking both of those into account where you have to, where you determine which is faster, okay, by taking both of them into account, okay? And so we'll see, okay, so we just wanted to say that. Okay, here's one last thing then, I think, and then we take a break. So what's the activation energy of a reaction for which the rate constant doubles on going from 20 degrees C to 30 degrees C? So I said a rule of thumb, this is something that my lecturer told me when I was learning kinetics, right? That the rate of reaction doubles for a 10 K rise in temperature. So here it is, right? a 10-degree rise in temperature. So we've gone from 20 to 30 degrees, okay? So if we use the Arrhenius equation, we have K is equal to A e to the minus EA over RT, and then we have the rate constant at temperature 1, that should be maybe T1, not 1, okay, over the rate constant temperature 2 is equal to A at T1 over A at T2 e to the minus EA over RT1 minus EA over RT2, okay? And so the A over A cancel because the frequency factor is the same, and we have the rate constant at T1 divided by rate constant at T2 is the exponent of minus EA over R times 1 over T1 minus 1 over T2, okay? And so we have log of K1 over K2 is equal to minus EA over R times 1 over T1 minus 1 over T2, okay? If we go here, we just plug it in then. So it doubles at T2. So log of a half is minus EA over 8.314 times 1 over 293.15 minus 1 over 303.15, okay? When we solve that, the activation energy is 51.2 kilojoules per mole. So there actually is just one activation energy for which a rate constant will double for a 10 K rise in temperature. And that activation energy is 51.2. Why is it a good rule of thumb? Because actually for a lot of biological processes, the activation energy is about 50 kilojoules per mole, okay? So that's why people say, oh, you know, growth will be twice as fast at 30 degrees compared to 20 degrees, for instance, right? Why? Because it's a biological process, like we'd say grass growth or something like that. Now, maybe after a while, you probably start to kill the grass if it's 30 degrees C, but anyway. Okay, I hope you understand what I'm trying to say. Okay, so I'm going to leave it at that. I have enough with the temperature dependence. We'll come back and we'll talk about pressure dependence. Okay.